All right, so I think it's time for the last talk of the morning session. The speaker is Andrei Egorov from Lobachevsky State University. He's going to talk about volume bounds on polyhedra in Lobachevsky space. So, Andrei, over to you.
Thank you. So my talk is called Volume Bounds on Polyhedra in Lobachevsky space. I thank the organizers for opportunity to talk today. I will mostly talk about right-handed polyhedra, but in the end, I will just touch a little bit more general case. So we consider right-handed polyhedra in three-dimensional hyperbolic space. Right-handed means that all dihedral angles are equal to pi over 2. And we suppose that vertices of this polyhedra can be of two types. The first type is finite vertices, means that this is just an ordinary vertices, ordinary points in hyperbolic space. Or ideal vertices, this is the vertices which lie in the boundary of Lobachevsky space. And we can now group all right-handed polyhedra into three groups. First group is a compact polyhedra when all vertices are finite. The first one, another one is ideal polyhedra when all vertices are ideal, and the mixed case when we can have ideal vertices and finite vertices. And it's known that hyperbolic polyhedron is uniquely defined by its dihedral angles and combinatorics. And Andreev's theorem gives the connection between dihedral angles and combinatorics. And in this slide, you might see Andreev's theorem for the case of right-handed polyhedra when all dihedral angles are fixed and equal to pi over 2. And in this case, the polyhedron P can be realized in hyperbolic space as a right-handed polyhedron if the following conditions hold. If the following conditions hold, the first condition is that this polyhedron P has at least 6 faces. The second condition that each vertex of this polyhedron has degree 3 or degree 4. And moreover, vertices of degree 3, they correspond to the finite vertices, and vertices of degree 4, they correspond to the ideal vertices. The third condition that if we have 3 faces of the polyhedron and the first 2 intersect, and intersection is an H, and the second 2 also intersect, and the intersection is an H, and these 2 edges have distinct endpoints that the first and the third face should not intersect. And the last condition.
Excuse me, you wrote union instead of intersection.
Oh, sorry, I just mistaken. Yeah, sorry. Yeah, it should be intersection. Thank you. Yeah, it should be intersection. Yeah. Yeah. In the last condition, if we have P should not have a force circuit. That means that if we have a polyhedron and we consider a closed curve on the boundary of this polyhedron, which separates 2 different faces of this polyhedron, then this curve should intersect at least 5 edges. That's the last condition. And firstly, I will talk about ideal polyhedra. So in ideal case, all vertices has degree 4. So they will have their graphs are 4-valent. Firstly, an example, actually a family of examples, a family of ideal antiprisms. An ideal antiprism N can be constructed in the following way. We take an n-gon and another n-gon and connect them by the layer of triangles. For example, here in the picture on the right, we have a polyhedron A4. We have a 4-gon on the top, 4-gon as an outer face, and they are connected by triangles. And on the left, there is a A3, which is actually same time an octahedron, and same time actually the smallest possible ideal right-handed polyhedron. For each of these antiprisms, we have an exact volume formula, which is proved by William Thurston. And I will notice that for other ideal polyhedra, we don't have an exact volume formula. And if we choose some random polyhedron, it's usually hyperbolic polyhedron, it's usually hard to find an exact volume formula. That's also why it's maybe interesting to consider volume bounds. And another interesting thing about antiprisms is that all other ideal right-handed polyhedra can be obtained from antiprisms by applying one operation called H-twist. This operation is performed the following way. We have a polyhedron, as here on the left, we choose some face of this polyhedron, which is not a triangle. It can be 4-gon, 5-gon, etc. We choose 2 edges of this polyhedron, or of this face, which are distinct. They are not adjacent. And we delete these edges, create new point, and connect the ends of the deleted edges with this point. And this way we obtain another polyhedron which has one more vertex than the initial one. And the theorem states that if we have a ideal right-handed polyhedron, that it is either an antiprism or it can be obtained from an antiprism A4 by sequence of these moves. And in this picture, just an illustration of this theorem. Here, dots are polyhedra, and the edges are an edge between 2 dots means that the upper polyhedron is obtained from the lower one by an edge by the separation. And we can see that in the bottom here, and the polyhedron A4, and all others can be obtained from here. Now I'll talk about volume bounds. The first volume bounds were proved by Christopher Atkinson in 2009. He used a number of vertices of the polyhedron to approximate the volume. So in this volume bound, if we have an ideal right-handed polyhedron 3 with V vertices, then the volume lies between 2 numbers, both linearly dependent on number of vertices. And the number, the constant V8 is just a constant. It's actually the volume of octahedron. And moreover, the upper volume bound here is asymptotically sharp. It means that we can't, if we want to improve this volume bound and stay and have volume bound of this form, then we can't change this coefficient V8 over 2. We can only change the free term. And in 2020, me and Andrei Egorov, we improved the upper volume bound by proving this coefficient, by making it smaller. No, actually larger, model larger, but yeah. And just recently, me and colleagues, we improved the upper volume bound, again, but only for the case when number of vertices is larger than 24. This is the first item of this theorem. And also, I can notice that we can consider some subclasses of ideal polyhedra, and for them, the volume bound again can be proved. For example, here in item 2, we consider ideal polyhedra with only triangular and quadrilateral faces. Then the volume bound can be improved independently for this case. And also, we can consider some other parameters of polyhedron, not only number of vertices. For example, as in the third atom, we approximate the volume by the number of vertices and a parameter k, which is actually size of some face of the polyhedron. So if the polyhedron has a k-gonal face, then this volume bound can be is true. Now I'll give some idea of the proof of this theorem, actually of the first item. So the idea is to decompose the polyhedron into tetrahedra. And this decomposition is obtained the following way. For example, here in the picture, we can see in the left, it is an antiprism A4. First step is to choose a vertex of this polyhedron, for example, a vertex V1, and fix it. Then we just consider a face of the polyhedron and consider a projection of this vertex, fixed vertex, to this face. We obtain the point U. And the next step, we just also, as in the picture on the right, we project this point U into the edges of the considered face. Yeah, we obtain this tetrahedra. And we do the same thing for all vertices of the polyhedron. And they obtain the decomposition as here in the picture on the right. And it may be noticed that for some vertices here, this decomposition depends on how we choose the first fixed point, first fixed vertex. And we might notice that in this decomposition, some vertices of polyhedra, they lie exactly in 8 tetrahedra, and some vertices lie in less than 8 tetrahedra. For For example, the vertices V2, V3, V4, they lie less than 80 trihedra, and vertex V7 lie in exactly 80 trihedra because it's actually kind of far away from the vertex V1 chosen in the beginning. And the idea of the further proof is to just to choose the initial point V1 to maximize the amount of vertices which lie in less than 80 trihedra. And by doing this, we prove that if number of vertices is bigger than 24, then this volume bound can be proved. Now I'll talk about compact case. In compact case, the Andreev theorem can be stated this way, that a polyhedron is realized as a compact rectangular polyhedron if and only if any vertex has degree 3, any face has at least 5 sides, and there is no 4 circuits. And firstly, I'll show this picture shows how many polyhedra, compact rectangular polyhedra, we have for different number of faces. For example, for 12 number of faces, we have only one polyhedron, which is actually a hyperbolic rectangular dodecahedron. And for example, for less than 12, we don't have any examples of rectangular polyhedra, compact rectangular polyhedra. And for example, for 24 faces, we have 6,800 polyhedra. The example of compact rectangular polyhedra is maybe the family of Löbell polyhedra, which is kind of similar to the antiprisms. In ideal case, the Löbell polyhedron Ln for n larger than or equal to 5 can be constructed the following way. We take 2 n-gons and connect them by 5 gons, by pentagons. And for each of these Löbell polyhedra, we have exact volume formula. And they have the similar property as an antiprisms. In ideal case, we can construct all other compact rectangular polyhedra from Löbell polyhedra by applying, in this case, 2 operations. The first operation is a composition. We just have 2 compact polyhedra. They have a k-gonal phase, F1 and F2, and we combinatorially compose them together along this phase. This is the first operation, and the second operation is just an addition of an edge. We have a polyhedron, and we just choose a phase in this polyhedron, which is not a 5-gon, it can be 6-gon, and we just add a new edge. And we just need to look that the new polyhedron doesn't have 4 gons in triangles because they are restricted. They are forbidden by Andreev theorem. This is the second operation, and the theorem states that if we just take all Löbell polyhedra, then we compose them together, add edges. This way we can obtain all other compact polyhedra. And moreover, each of this operation increase the volume. Increase the volume means that if we add an edge, volume is increasing, and if we compose 2 polyhedra, then the volume of the resulting polyhedra is going to be larger than or equal to the sum of the volumes of the initial 2 polyhedra. And the similar thing about volume bounds here, Atkinson proved the volume bounds for compact case also. He also used the number of vertices to approximate the volume. And in 2020, me and Andrei Egorov, we improved the upper volume bound. And just in December, me and colleagues, we improved this volume bound, but only for number of vertices larger than 80. This coefficient free term can be improved. And also can be proved some volume bounds which use not only the number of vertices, but some other parameters which of the polyhedra. And also we can consider in the mixed case, the same thing here. In the mixed case, we can have vertices of ideal vertices and finite vertices. So here in this theorem, the number of ideal vertices is called V infinity, and the number of finite vertices is called VF. And we improve this volume bound, then this number of vertices means the sum of ideal vertices and finite vertices is larger than 17. The general case, Andrei Yuryevich Vesnin already talked about that a little bit in his talk. In the general case, there is a Belletti theorem which states in particular states that if we have a hyperbolic polyhedron, then this volume of this polyhedron is actually less than the volume of some specific ideal right-angled polyhedron. And since we have the volume bounds for ideal polyhedra, we can write the volume bound for just more general polyhedron, hyperbolic polyhedron. Here it is, and it's expressed, it uses number of ages to approximate the volume. And at the end, I will say, talk about a little bit about links. There is we know that if we consider a hyperbolic link, let's define let's call the link right-angled if its complement, which is equipped with hyperbolic structure, can be decomposed into right-angled polyhedra. We know such examples such as Whitehead link or Baramian links. And there is a question, is there links with one component, means knots, which are right-angled? And the conjecture that there are not right-angled knots. And it can be also verified for knots up to 11 crossings by just comparing the approximate volumes of knots, and there are approximate volumes of ideal polyhedra. We can just compare them and find out that for 11 crossings, and actually I try to do that for 13 crossings, the conjecture is true. Okay, thank you for listening. I'll stop here.
Thank you, Andrei, for the wonderful talk. Are there any questions or comments? Okay, so if there are no questions or comments, let us thank Andrei.